Hello again. Yes, this is the lab. I just like to start out in the classroom. Just because it's quieter in here, it's a little brighter in here, and I have some clean tabletop space that I can use. So today, what we're going to talk about is data communication, data streams, if you will. When we were talking about inputs, we talked about what goes on the network wires, the voltage signals that go on. We talked about things like binary code and stuff like that. This part of it, I'm more interested in the physical hardware that makes up the network. So that's mostly wires and modules. So we'll do a little bit of looking at what those wires look like, how they're configured. There's a couple different ways they're set up. We have star configuration. In a star configuration, everything comes back to a central point. And then we have ring configuration. In a ring configuration, the network goes from this module to this module to this module. So during the lecture portion, I'll show you this on ALLDATA. And in here, I'm just going to kind of build very, very crude examples of what those networks actually look like. We've heard the word bus talked about when it comes to networks. Information bus, data bus, bus inputs. So what exactly is a bus? And it's really a lot simpler than you think. A bus is just an electrical path that a lot of different things can attach to. So what I have here is this bare copper wire. And attached to the copper wire I have 6 separate branches branching off of it. This is what we would call a star configuration. In other words, everything comes back to a central point, the central point being this copper wire in the middle here. So the point with this is anything that's put on the bus, so on this copper wire, is available to any of the nodes, any of the computers attached to the bus. So maybe this wire goes out to your ABS module, and this one goes to the instrument cluster, and this one to the PCM, and this one to the body control. Maybe this is anti-theft. Maybe this one here is airbags. But because they're all attached to this common bus, they're all connected together. So I have the voltmeter set up here, and my power supply, I have about 13.5 volts. So if I take this voltmeter lead here, obviously here coming into the bus, got my 13.5. And then if I go down the line, here's my first node. It's got the same voltage available to it. Second one, same voltage. Third one, same voltage. Fourth one here, same voltage. Fifth and sixth. So what you're seeing is that voltage put on the bus, in this case it's just a steady 13.5 volts, but voltage put on the bus is available to every node attached to that bus. So in this case I have 6 of them, and they would represent 6 different computers or modules. So remember the oscilloscope from another lab, and I just have it set up here again just to remind you. Volts is up this way. Right now it's set for 2 volts per division, so 2, 4, 6, 8, 10. I have a 9-volt battery here. If I just hook my scope up to that, it reads about 8.5 volts. So, whoops, just hooked on here. Just to the 2 terminals on my battery. So, we're not going to use a 9-volt battery. What I have here is a signal generator board. So I have this signal generator board set up right now. It's putting out a digital square wave signal, and I'm just going to focus in on the scope screen and see what that looks like on the scope. So here you can see I have a digital square wave. It's off here, on, off, on. I can change the timing a little bit, make these a little bigger or smaller, maybe make it a little bit easier to see. So that's the signal that's coming out of the board as measured by the scope, and it's putting out about 5 volts, 2, 4, little under 5. So I'm going to unhook my scope lead from the signal generator and hook it to one of the nodes coming off of my bus here. So you saw before that when I put about 13.5 volts on this wire on the bus, we saw that 13.5 volts here, we saw it, here, we saw it here, we saw it at every node coming off of that star configuration bus. They all come together to one spot. So I'm going to take my oscilloscope test lead, and let me just hook it, for example, to the yellow one here, and then we'll go back to our screen and see what we get. So now, instead of hooking the scope directly to the signal generator board, what I've done is I've taken a wire from this board and run it into my information bus here. So we're hooked up right here, injecting that signal down this entire wire. So what we want to look at is I have my scope hooked to the yellow one, and if we look at the oscilloscope screen, give me a second here, we'll do that. Get focused in on it. See if I can focus it. We see the exact same signal here that we saw coming directly off the board. Now, if I change that oscilloscope lead to the blue wire, we're going to see we have the exact same signal on the blue wire. So what you're seeing here is an example of if data is put out on a bus, in this case it's just a digital square wave signal, data is put on that bus, it's available to every computer that's attached to that bus. My apologies for the crude mock-up here, but I got to work with what we have. So what you're looking at here is a 2-wire network, and it's a ring topology. In other words, everything does not come together to a central location. Notice for the instrument panel cluster to have access to the PCM, it's going through the ABS module. So there are some advantages in speed and stuff like that, but the downside here is if this module goes off the network, we no longer have a connection to the instrument panel cluster. So we did experience a problem like that last semester, I think, with the one BMW, where the cluster went bad and it interrupted the communication with some other modules like the PCM, the anti-theft module. Anyhow, let me point out what we have here. So instrument panel cluster, analog brakes, powertrain control module, and body control module, each connected to the other by a pair of wires. So this blue circuit is the same throughout the entire network. The yellow one is the same throughout the entire network. And notice that they end at the data link connector, pins 6 and 14. So we'll look at the wiring diagram for, I think it's a 2010 Chevy, where we see the high-speed CAN network. You'll see that it comes to the data link connector at pins 6 and 14. So if we plug a scan tool into this car, through these 2 pins, that scan tool is able to access all of these modules that are on that network. Now, most cars have multiple networks. They have single wire, they have 2-wire. We'll probably talk about that some more in the lecture portion of it, because I can bring up all data a little more clearly on that. Something else I want to point out, at each end of the network here is a resistor. We'll see these in the wiring diagrams too. So we've got a terminating resistor on that end. We have a terminating resistor on that end. They could be in the wiring harness, or they may also be built into the end modules. Like it could just as easily be inside the PCM instead of outside the BCM rather, instead of outside the BCM. Same with this one. It could be built into the instrument panel cluster. You'll see both. In fact, I think the car we're going to look at, you'll see one of them is embedded in a module and one of them is just in the wiring harness. So what I want to do now is, this is just an overview of what a network looks like. It's really simple. It's wires, and Nothing too complicated. So if something goes wrong with the network, we can actually just ohm meter check these wires. And also with the scan tool, we can see which modules we do have access to and which modules we don't have access to, and sometimes that can provide a clue for us. So I want to stop here and talk more about these resistors and how you can tell if they're okay or if the integrity of the network is good just from using an ohm meter at pins 6 and 14. So I'll get back to that in a while. Meantime, we need to talk something about parallel circuits, a little review from Basic Electrical. A little review here on parallel circuits. I have here two identical resistors. And first we're going to measure what the resistors are, resistance individually. And then I'm going to hook them together in parallel and see what the combined resistance of the two in parallel is. And we'll look at series too. So let's start by switching our meter on to ohms. And we'll just look at the resistance of one of these. And we can see that it's about 15 kiloohms, so 14.97 k ohms. And the other one, if I can get it to stop running away from me here. Is about the same, 14.9 kiloohms. So we know if we connect resistors together in series, so let me just try to hook these together like so. All right, maybe we'll just twist them. The resistance is going to end up the sum of the two. So it should be about 30K. We've got 29.86 kiloohms there. So what happens when we put these together in parallel? So let's twist these together. And we'll twist these together. And if you remember right from electrical class, when we have two resistors in parallel like this, and they are identical, the combined resistance is going to be about half. We've got about 7.5 k ohm here. So what's happening is, we have one resistor, we have a path for current to flow. When we add in the second, we are doubling the path we have for current to flow, so that reduces the resistance down to half of what it was with just the one resistor. So that's a quick review of parallel circuits, and we'll see how in a CAN network, some of them use terminating resistors, and those resistors are each 120 k ohms. So when they're connected together in parallel, which they are, the resistance on that network should be about 60 k ohms. So here we are back now to talk about our little network. Like I said, these two wires are essentially a parallel network. The two resistors are exactly like what I showed you a minute ago on the bench. In a CAN network, control area network, each of these resistors is 120 k. So if I measure the resistance of this network, what do you expect it to be? If I stick a voltmeter in pins 6 and 14, and I have 220 k ohm resistors wired in parallel, that's right, boys and girls, 60 k ohms. If I read 120 k, that tells me I'm only going through one of these resistors. In other words, one of my branches of the network is open, disconnected, or one of these resistors is open. So I expect to see 60 k if I put an ohm meter from pins 6 and 14. And we will try that exact thing on a real vehicle in a little bit. So we talked about star configuration and ring configuration networks. This little connector right here, this is a junction point where all the different wires from different modules come together in this star configuration network. So what's connecting them all is this little metal comb. When you pull this out, all the different modules are unhooked from each other. So each one of these wires goes out to something different. And when we plug it all together with the comb here, then it becomes one network. So you could almost call this the bus, but the entire thing is the bus, really. Today we'll be using this Jeep Cherokee to demonstrate some of the network topology things using WiTech. So I'll bring up the wiring diagram, and I'll also bring up the live WiTech view, and we can see what it looks like on the wiring diagram and what it looks like in the network topology view on WiTech. So here I brought up the ALLDATA, the wiring diagrams for the information bus on this 2014 Jeep Cherokee with 3.2 V6. So we'll start with ALLDATA with the wiring diagrams, and notice we have marked this here. We have three different buses here. We've got the LIN bus, CAN-C, and CAN-IHS bus. So I'm going to start in the middle here with the CAN-C bus system. And let's take a look at what kinds of modules are connected to this and what kind of wiring there is. So I'm just going to zoom this, bring it up full screen for us so we can see it better. And so notice CAN-C is a two-wire module, or a two-wire bus rather. So I've got plus and minus, basically the signal and the ground, going from the module, the steering control module, into, now it doesn't say, but we'll go to the next one here. Here's the rest of it. So that's the star connector. Now, the star connector, like I just showed you a little while ago, I showed you on an Impala. That's where all of the networks come together, kind of like that bare wire I had on the bench top, except for this has two wires instead of just one. So this is just like a central connector that all of the different wires come into, so that, for example, this radio module can talk to other modules through this star connector. So if we look at the WiTech, this is what the network looks like here. And notice we've got different color wires here. So these are blue here, and these are more of a black or dark gray. And if we look at the legend, so we can see that the CAN-C bus is what's in black here, and the interior high-speed bus is on the blue, and the star connectors are these black or gray-looking boxes. So looking here, you'll see that all of these modules on the right side here. So I just grab these. So these, they're all connected into one star connector. And since they're on the blue, remember what the blue was. Take this off here. The blue was the interior high speed, IHS, CAN IHS. And then that's connected to another star connector, and more IHS bus modules are connected in there. And that goes back to the BCM, and it goes out to the data link connector. So let's look at the BCM for a minute. The BCM has a feed into the star connector for the IHS bus, and it also has a feed into the star connector for the CAN-C bus. So the BCM has access to both of these buses. All of these modules are able to talk to the body control module. All of these modules are able to talk to the body control module. If you look at the instrument panel, same thing. It has connections going both ways. The radio has connections going both ways. And most importantly for us, I guess, the data link connector down here at the bottom is tied into both on different pins. So one thing you'll notice, or I'll point out anyhow, is that the reason they have two different networks, some of these things need to be more real time. So higher speed communications, where others not so much. So driver's door module, for example, not critical, not a safety issue. PCM, the what you call it, transmission control module. ABS, those are more time critical things. So this CAN-C is going to be a higher speed network, and the CAN-IHS, not so much. So going back to the wiring diagrams, we're seeing our CAN-C bus here, 2 wires going out to everything. Adaptive cruise control. The radio we saw was on both. The cluster was on both modules, or on both networks. So we close this, and we'll go back. And we'll click on the IHS. Okay, my mouse is not behaving. So notice that's also 2-wire network. Now on YTech, it doesn't really show you that. It's just showing you the connections between. It's not indicating that there's 2 wires. Don't want that. So look, we've got the radio amplifier. Here's the data link connectors. It looks like pins 3 and 11 give us access to the IHS bus. Here's the instrument cluster. If we actually go to the data link connector pin out, let's see if we can find that. So that's the connector, 1 through 8, 9 through 16. 16 is always the power. Certain ones are always ground. So it shows us, 3 is interior high speed plus, 11 interior high speed minus, 6 and 14, those are the CAN-C plus and minus. So when we plug a scan tool in, as long as it can read those pins, then it can access all of those modules. Go back to the diagram a minute. And notice we have a third information bus, the LIN bus system. So LIN bus is basically smart sensors connecting in. So what do we have here? So battery current sensor, this siren, the light range sensor, intrusion module. These are little smart sensors basically, and they're able to talk back into the rest of the network. Back to the YTech here. I don't know if it shows us. Let's look at the legend here. It really doesn't show us the LIN bus at all. So, here they're not really showing us precisely what pins these things go to. You can remember the CAN-C bus went to 6 and 14. The IHS bus went to 3 and 11, I believe. Pin 16 is hot. We'll talk about that a little bit more in the lecture. I don't want to spend too much time sitting here lecturing during the lab, but I just wanted to show you, out in the shop where I could plug in YTech and get a look at it here to see that, the way it's drawn just looks like single wire, but when you look at the actual wiring diagram, you can see there's 2 wires going to each of these, and there are 2 separate CAN buses on this car. One is more mission critical type of modules where the higher speed is important, and then the other is this interior stuff. And in some instances, they're able to talk to each other, or at least modules are connected to both of them. So the radio, the instrument panel cluster, the BCM are connected to both. They both use these star connectors like I showed you under the dash of that Impala. Not saying they look exactly the same, but the idea is the same, that this is where everything kind of comes together in a star configuration. And so, in other words, back to a central point. So that's about it for this. And we'll do some other stuff before we wrap it up. What I have here is a breakout box that's designed to allow us to get into the data link connector without actually sticking meter leads into the connector itself. This plugs into the data link connector, and then I have access to all 16 pins on these little test points here. So I'm going to plug that into the data link connector, and then we can use our meter in those points to see what's going on. I've connected a breakout box to the data link connector, and what that does is allows us to access the pins of the data link connector and therefore the different circuits in the network without actually jamming meter probes into the data link connector itself. So I'm going to use this breakout box to do a couple of things. Right now I have the battery disconnected, and I've looked up the specs for this network, and what it tells me is total resistance of CAN networks can be measured with the battery disconnected. The average resistance is approximately 60 ohms. The termination resistors are integral to the star connectors. So I showed you this on the bench. I talked about 120 k ohms. Apparently these are 120 ohm resistors in parallel, and the total resistance you should measure is about 60. So let's see what we get. I have the battery unhooked, set our meter to ohms, and I'm going to go from pins 6 and 14. And we have just over 58 ohms, pretty close. And now I'll go to pins 3 and 11. Pins 3 and 11, 61.7. So the resistance seems to be about what it's supposed to be. So the other thing they give us is voltage, both with the bus idle and with the bus active. So the CAN-C bus circuits, when they're asleep, should be 0 volts. When the bus is idle, about somewhere around 2.5 volts, and when the bus is active, the high will be 2.6 to 3.5, and the low will be 1.3 to 2.3. And then the IHS bus is a little bit different than that. So what I'm going to do is hook the battery back up and switch over to volts and see what we get. So I've hooked the battery back up and I've switched over to volts. My common voltmeter lead, the black lead, I've put into pin 5. Pin 5 is the signal ground. And the red lead now, I'm in pin 6, which is the CAN-C plus. And it's reading essentially 0. It says 16.7 millivolts. The CAN low, or the CAN minus, pin 14, is essentially reading nothing also. So when I turn the key on, the bus should go active, and we should see on the high somewhere between 2.6 to 3.5. So I'm going to go back into my CAN-C high or plus and go turn the key on. Didn't really intend to start it there, but so that's the high, and our specs are 2.5 to 2.7 volts. We've got just over 2.7. The low should be 2.3 to 2.5, so let's go to the low. And we've got 2.240. So those fall pretty much in line. If the, I'm sorry, bus active, the high is 2.6 to 3.5, so we were right in there. Now, what makes the bus active? Well, anytime something happens, the bus is going to go active. If we let this sit for a while, the bus would go idle, and our voltage level would drop just a little bit. If it falls to sleep, it should drop back to 0. So that's the CAN-C. We'll do the same thing with the interior high speed. So the high on that is pin 3, and we're supposed to see with the bus active 2.6 to 3.5 also. So we're in that range, and then on the low or the minus with the bus active 1.3 to 2.3. Go over to pin 11 here. And it's just a little higher than what we're expecting, I guess, but not completely out of the question. Now I'm going to go turn the key off, and let's see how long it takes before this drops back to idle or sleep. We'll see how long this takes. I don't know how long I can wait before y'all fall asleep on me. You know, with the doors open, it's probably never going to fall asleep. Okay, I just now shut the door, and we'll see how long it takes for this network to start going to sleep. That was about 10 seconds, it dropped down quite a bit. Oh, I just saw the dash just woke up for some reason, and it came back alive again. Oh, now we're down to 0.5 volt. Dash is back out again. And now it basically went to 0. That's only 6 millivolts. That's as close to 0 as you need to get. So that was about a minute that the thing stayed alive. I don't know what that little glitch with the dash popping back on was. You couldn't see that on the camera, but I do know this vehicle has a really bad battery. I have a jump box hooked to it that may have something to do with the strange behavior. So I'm going to do this now, take this over to a General Motors vehicle and see if anything's different on that. That I think we'll just try for resistance. So I have the breakout box attached to the data link connector on this GMC, and I've got the meter set here. I'm going to switch this over to ohms, and we'll just plug into pins 6 and 14. and see what we get. So 61.3 ohms. That's pretty close to the 60 we expected. Now let's talk about what happens when something goes off the network. In other words, when a module maybe loses its connection. You know, what do you see? What do you see on a scan tool? What makes you start doing ohm meter or voltmeter checks on the network in the first place? So let me just adjust this a little bit. I've hooked the YTech up again. So let's see here. We'll log back in. And we have the Cherokee out there. So let me just click on that. And this vehicle has a lot of diagnostic trouble codes. I'm not really worried about most of them. I just want to look here at this one. This is a U code. So network codes are U codes. They indicate that there's some sort of a communication problem. In this case, the code is coming from the instrument panel cluster. So the thing that's important to remember is the code's coming from the instrument panel cluster. The problem is absolutely not with the instrument panel cluster, because how could it talk to the scan tool? How could it send a code if it was off the network? So it's telling you something else is off the network. And what it's saying is it lost communication with the TCM. Going back here, so here's the transmission control module. What network is that on? Well, we look at the legend here. It's the dark. It's the CAN-C, so that's the high speed, the 500K, as opposed to the interior high speed, which is a confusing name because it's slower than the CAN-C. This is only 250 kilobit. Anyhow, here's the cluster in the middle, and it's lost communication with the transmission control module. So it's not saying that it's lost communication with the PCM, electronic power steering, or anything else. So odds are the cluster's connection through these star connectors and all that is good. The problem currently lies with the transmission control module or its connection into the network. So what we would have to do, let's bring up all data again here and get that vehicle up. That's 2014 Jeep Cherokee with the 3.2. Let me just increase the size of this a little bit. There we go. And if we look at electrical diagrams, powertrain management, right, we've got the CAN-C bus. So that's what we're talking about. And on that CAN-C bus, let's see if I can find where that transmission control module is. Hard for me to read here. Oh, steering. There we go, transmission control. So something we could do, right, is we could take an ohm meter from pin 47 of that transmission control module. So that's the CAN-C minus. That's pin 14 on the data link connector, so we could go straight to there. Or, we could go to the star connector, locate that, and find pin 2 on the star connector, and just basically do an ohm meter check of this yellow wire here. Actually, I'm on the wrong one here. So this is for the 2.4, right? 2 liter, 2.4. Over here is the 3.2 liter. So same thing though. Pin 47, CAN-C minus on the data link connector. That's going to be pin 14. CAN-C plus is going to be pin 6 on the data link connector. So we could go all the way to the data link connector and see if there's a connection there. If there's not, we can check the smaller branch of it just between the transmission control module and the star connector. So we would have to locate this star connector, access it, and just put an ohm meter right in that pin there. Pin 1 should have continuity to pin 34 of the transmission control module. So it's not complicated, they're just wires. So if the wires check out good, that means there's a problem with the module itself. It has circuitry inside that's responsible for transmitting and receiving data over the network. And so if the wires are good and the module has dropped off the network, then the problem lies with the module itself. Or, just as important, maybe the module lost power or ground. So if the module loses power or ground, obviously it's going to go dark and lose communication with the rest of the vehicle. Let's talk about what we've learned in this lab. We started on the bench in the classroom here. First, you saw me construct a admittedly really crude single wire network, information bus or data bus out of just a solid piece of copper wire. So that's not what they really look like in the car, but what you were able to see is that a bus is essentially just wires that all kind of connect together. So next thing we did is I showed you again a really crude idea of a 2-wire network. And what you saw, and I just did 4 or 5 modules, little post-it notes, and ran them to the data link connector. So you can see, you had pin 6 and 14, and you had terminating resistors. In both vehicles we looked at out in the shop today, the terminating resistors were 120 ohm, not 120 k ohm. So next I showed you a little review of parallel circuits with the two, I think they were 15 k ohm resistors. Each one measured right around 15 k. But then when I put them together in series, you saw it measured 30 k. So series circuits, the resistances add up. But parallel circuits, when I added that second resistor in parallel, it cut the total resistance of the circuit in half. It went down to about 7.5 k. Next thing we did was moved out into the shop on a 2014 Jeep Cherokee, not a Grand Cherokee, but a Cherokee. And we looked at several different things with the network there. So first, we brought up YTech, and we looked at the overall topology of the network, how things were connected together. We saw that there were 2 CAN networks. There was the CAN C, high speed, 500K, and the CAN IHS, 250K, a little bit lower speed. And we talked about why some modules need to talk at high speed and why some are okay at that lower speed. Mostly it's really, how real time does the data have to be? If I step on my brakes, I want my PCM to disengage the cruise control immediately. I don't want any kind of lag or any kind of delay. But if I'm just doing climate control or something, not really critical that things happen, fast like that. So we didn't talk much about the LIN network, just a quick look at that, and that's really just smart sensors. So then, next thing we did was we took some measurements on that CAN network, on the 2 CAN networks on the Cherokee. We looked at resistance, and we saw those networks had a resistance right around 60 ohms. So again, parallel 120 ohm resistors gave us 60 ohms total on the circuit. Then I went over to a GMC, same thing. We looked at the wiring diagram for that. 2 parallel 120 ohm resistors. Total resistance at the data link connector we measured was about 60, give or take a little bit. So another thing we looked at was the voltage on the CAN network on the Jeep again. And I had a chart, I didn't show it to you, but I was looking, and it was telling us what the voltages should be when it's idle, when everything's asleep, and when it's active. So we started with it asleep. We had basically nothing, a couple, tiny little milliohm sort of, or millivolt sort of voltage levels. And as soon as I turned the key on, that went up to 2 or 3 volts as everything woke up. And then I set a timer, and after I turned the key off, closed all the doors, it took about a minute for everything to fall back asleep and for that bus to go idle again. And we can see that on the voltmeter. So last thing, at least I think was the last thing, was we talked a little bit about U-codes. You know, what is the self-diagnostics for the network? And essentially what it is, if a module drops off the network, another module is going to set a code. The module that drops off the network is not going to be the one that sets the code. So that about wraps this up. Your report should have all the numbers, should explain everything. I gotten some reports on the other labs that stopped at a certain point, didn't cover the entire lab that we did. Like, for example, they talked all about what we did on the bench and then nothing about what we did on the car, or just about one thing we did on the car when we did a lot of different things on the car. So this lab, we did a lot of different things. We did bench stuff, we did car stuff, we did it on a Jeep, we did it on a GM, and we took measurements, we got numbers. So plenty of information. You should be able to come up with a good 2 pages on the report for that. I've posted this during our April break, and we're not allowed to have anything due during the April break. So I'll send you an email telling you when the due date is. It's going to be sometime the week after break ends. So I think break is over on the 18th. So the week following that, your report for this will be due. In the meantime, stay home, stay safe if you can. I know some of you are working like nothing's changed, and they've officially said we're not coming back, so I will not see you face-to-face again unless you have another semester to do. But hopefully everybody that's supposed to graduate will, and stop by and visit next year.